All right, here we are. We're gonna do the backside of this, but first let's talk about where we left off in the last video, and it's this. What's the relationship between x squared and 2x? Same relationship between x cubed and 3x squared. Okay, time to figure it out. If you don't know it, pause the video, figure out what the relationship is between these two, but I think you know it, and here it is. The derivative of x cubed is 3x squared, okay? If the derivative of x cubed is 3x squared, you can't see me, I'm off camera, but I'm just so excited about this, I'm shaking, and that's actually true. Like all of a sudden, I'm like, this is great. So the derivative of this is 3x squared. But when I used 3x squared, 3t squared, if you want to go that route, 3x squared, 3t squared, and I used that to find the accumulated area, I got what was its, let's use a word for it, it's antiderivative. So like the derivative would go this way, so the antiderivative would go this way. Okay? We just took an antiderivative whether you realized it or not. It's great. I love this. I love this. Okay. So when I take the integral of some function, I get the thing that if I took its derivative, I'd be working backwards. Okay, that was a little clunky in the way that I worded it, but we're gonna make some sense of it here. Okay, I'm gonna just write a few ideas down, and I'm just cranking out a few little thoughts. An integral, it'd be great if I could spell it, an integral takes an antiderivative. An antiderivative is that thing you would say, oh, the derivative of this will take me back here, okay? So an integral takes an antiderivative. Let me crank out another little statement that's gonna work pretty well. Integrals and derivatives are inverse operations. Okay, this is a huge idea, y'all. This is huge, and it's a lot to wrap your mind around, because all of a sudden, if you were anything like me first time you saw it, you're like, how in the world is there a relationship between this, whose derivative is clearly 2x, but then if I find the accumulated area, I get the antiderivative, right? Like, how is that even a thing? And now we're cranking out all these crazy sentences. An integral takes an antiderivative. Finding the accumulated area takes an antiderivative. Integrals and derivatives are inverse operations. You know, like addition and subtraction undo each other. Integrals and derivatives undo each other. They are inverse operations. It's a lot to take in, seems overwhelming, so let's keep drowning. Let's go. The fundamental theorem of calculus for derivatives. Okay, there's more than one wording of the fundamental theorem of calculus, more than one thing we can glean from it and get from it, but this is the big idea for now. If some function is continuous and g of x equals the integral from a to x of f of t dt for all x in the interval from a to b, then derivatives and integrals are inverse operations. We actually just wrote that in a slightly different way. Then what? Then what, okay? Derivatives and intervals are inverse operations. This doesn't finish that sentence. That's a capital letter. I read it that way, but that is not what I intended. Here we go. If a function is continuous, okay, we have continuity, and g is an integrally defined function. I have defined this function to be the accumulated area for all x in some interval, then if I took the derivative of this side of the equation, then I would get something on the other side. Okay, whatever you do to one side, you do to the other. Okay, you learned it in middle school. Whatever you do, you add 3 to one side, add 3 to the other. Take the derivative of the left, take the derivative of the right. The derivative of an integral, they're inverse operations. So I get what I had to start with. Y is into t, Why isn't it a t? That will be explained later, but this is the big idea. If g is an integral, then g prime is the regular function, the original function, if you will, okay? I sometimes write it kind of as a list of things, and you're gonna see that in the next few examples, well, after this page, you're gonna see that in some other examples in just a few minutes. All right, here we go. We're gonna run with this idea. Very quickly though, let me kind of reinforce this thing. I want you to see what's happening here. I'm gonna kind of use this idea and this example and just kind of blend the two together. If I took the derivative of g of x, what would I get? Okay, the derivative of g of x is, well, this is g. The derivative of this is 3x squared. Don't panic about the t's, okay? Let's work with me here. Given g of x equals the area from 1 to x of f of t dt, where f of x equals 3, find g of 4. This idea is going to be pretty straightforward. Here we go. G of 4 is the integral from 1 to 4 of f of t dt. Well, they told me that the function f is really just 3. So whether we're using t or x or whatever, here's the deal. We've been through this. I'm going to have a function that goes over here at 3, and it goes from 4 to 4. It is 3 units wide and 3 units high. The final answer is the area of a 3 by 3 rectangle, square, so it's 9, okay? This idea was not used here. Hang tight, it's about to be. For f equals the integral of blah, 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 write an expression for f prime. All right, pause right there. They gave you f, and they asked for the derivative. So let's just go then. F prime equals, not even reading that part yet. We have to take the derivative of an integral. Then you're just going to get what you had to start with. They are inverse operations. Taking the derivative of an integral just simply gives you this little guy right here. There's an exception, we'll encounter it later. Why isn't it a t? Because this is a function of x. That's a simple answer. Okay, now find f prime of 2. Okay, great. F prime of 2 is 2 times 2 to the 4th. That would be 32. Let's keep moving. Given g of x is this disgusting mess that no one wants to do in their head, and f of x is the integral from 100 to x of g of t dt, write an expression for g prime of x. Okay. Oops, that should say f prime of x. I should say f prime. We're going to fix that. It'll be fixed in future editions of this. That's going to work on this one as well. So f prime here and f prime here. Okay. F prime. All righty, here we go. We're going to write an expression for f prime. Well, I'm going to take the derivative of this side. And when I do, I'm taking the derivative of an integral. Okay, I want you to notice something. A is just some number. Did A ever show up over here? No. But it's 100. Don't care. Don't care. Write an expression for f prime. Okay, fine, I'll do that. F prime is g. That would be tangent of x over the natural log of x plus 4 square root of x. That's it. Here goes number 4. It looks exactly the same. G is this. F is defined as the integral from 0 to 2x of g of t dt. Write an expression for f prime. Okay, I always have a hard time explaining this one, but we're just going to run with it and we'll see what happens. Final answer is f prime is equal to, oh, well, let's just use g then. So we're going to plug in, we're going to just use g. However, I want you to notice what happened here. This 2x, well, this x is going to go right there. That's kind of what we did. This 2x is going to go right there. And we're going to have tangent of 2x over the natural log of 2x plus 4 times the square root of, you guessed it, 2x. Now, we're not done. I want you to hold that thought. You just took the derivative of, watch, a composite function. Because of the chain rule, you have to multiply by the derivative of that inner function, and it is 2. It's a very tall 2 standing in the front. Okay? If you are lost, do not panic. Let's keep going. This is a weird concept. This is going to solidify things for us just a little bit. Simplify d dx, the integral from 44 to 3x squared of all this mess. Oh my goodness, what in the world? Okay, what are you doing? You're taking the derivative of what? An integral. Then you get what you had to start with. So let's write what you had to start with. A couple exceptions though. Sine of 9t? No. My input is now 3x squared. And it's also going to go there. Not there. So 9 times 3x squared over 1 minus 3x squared. Okay, are we done? No. This was a composite function. I think it's fairly obvious by the fact that we have this 3x squared, this kind of this inner piece. We have to multiply by the derivative of the inner function. That's how we do the chain rule. So we're going to multiply by the derivative of 3x squared, which is 6x. All right, last one. Fun stuff. Fun. I love this one. Okay, find the derivative of an integral. Oh, well, let's just plug it in. Looks like the last problem, we'll just plug a 3x squared. Look at that down there. That's not a constant. Not a constant. So check this out. Things are about to get a little wacky here. This is equal to something. This is equal to the derivative from 2x to, where do you want to stop? I'm going to stop at 0. What if 0's not in between them? Who cares? It works. Trust me. Of sine t dt. And we're going to add it to the derivative. You can split this thing up from 0 to 3x squared, just using some properties of integrals. Sine t dt, in parentheses if you want or not. Okay, I'm ready to take some derivatives if you are. Actually, I'm not. I'm going to do something a little crazy on this one. I don't like that this one is upside down from the way we're used to seeing it. Usually the number's on the bottom and the variable's on the top. So let's switch it over. d dx, integral from 0 to 2x of sine t dt. Can I just do that whenever I want? You change the sign, you can. Plus d dx, integral from 0 to 3x squared, sine t dt. Ooh, running out of room here, writing too big. All right, we're going to take the derivative of an integral. What do you do when you take the derivative of an integral? That is a fancy way of saying up here what we did say up here. We took the derivative of both sides. We took the derivative of the integral. We ended up with f. Derivatives and integrals are inverse operations. So here goes. 2x is going to go right there. 3x squared is going to go right there. And it's going to be negative something, leaving a little gap. Something's about to happen here. Negative sine of 2x, pause. This is a composite function. You just took the derivative of a composite function. You need to multiply by the derivative of 2x, which is 2. All right, let's keep moving. The derivative of an integral is, well, in this case, sine of 3x squared. Oh, wait, you just took the derivative of a composite function. The derivative of a composite function means I need to multiply by the derivative of the inner function. That would be 6x. We'll add a plus sign. There is my final answer.